Hello guys, this is codeNcode and this is the 7th lecture of this number theory series. And in this lecture we are going to study about how we can calculate the nth element of a recurrence relation in logN time. So before I start the lecture, if you guys think that the work I am doing is worth your praise and donation, so you can of course make donation. Anything you can, 100, 200 or 500, $1 million, whatever you can per month, you are welcome. And if you can't, that's completely okay. We all know we all are students, we don't make money for now at least, so it's okay if you can't make. And if you can, and if you think that this channel is worth your donation, so please, whatever you can, the details of the UPI is given in the description, so you can pay through Google Pay or UPI, whatever you can. So thank you for that, and let's start the lecture. So what is a recurrence relation? We are talking about how we can calculate the nth element of a recurrence relation. So we must know what is a recurrence relation. This is the definition. If I define that in simple words, so it is basically a sequence of numbers in which the nth number is defined in terms of previous k numbers of the same sequence. So if you take example of Fibonacci series, then nth element of the Fibonacci series is defined in terms of previous two Fibonacci numbers. So Fn is equals to sum of previous two Fibonacci numbers. So since nth element depends upon previous two elements, so the first two elements must already be defined, and we will call those two elements as base cases. Now since Fibonacci series depends upon previous two terms, so f1 and f2 must be defined so that we can calculate third, fourth and so on other terms of this series. So since Fibonacci depends upon previous two terms, generally we would call it k. So for Fibonacci, k is equals to 2 because it depends upon two terms. So for a general recurrence relation, we would assume that the recurrence relation depends upon previous k terms. For Fibonacci it's 2. Now while we were studying matrix exponentiation, in that lecture I have explained that using matrix exponentiation we would calculate the nth element of a recurrence relation in logN time. So what is the relation between matrix exponentiation and recurrence relation? For that we have to analyze this equation. These are two matrices. The first one is a row matrix of 1 cross 2 size. It would be a 1 cross k size matrix, where k, you know what is k. In the previous slide I have defined k. For Fibonacci series, k is equals to 2, so this is 1 cross 2 matrix. Now this is a for now let's call this a magic matrix, and if you multiply this base matrix or a matrix having element f1 f2, multiply it with the magic matrix, it would transform f1 f2 elements to f2 f3. Their indices increase by 1. Now if we take this newly calculated matrix and multiply it with magic matrix, it would again transform their indices by 1, increase their indices by 1. So the resultant would be f3 f4. So initially we had 1 1 here, 1 1 because f1 f2 are 1 1, so we had 1 1 here. We multiply it with the magic matrix, the resultant would be f2 f3, which is 1 2. Now we have taken the newly calculated result, which was f1 2, multiplied with the magic matrix, the resultant become f3 f4, which is 2 3. You see, from equation 1, if we replace the value of f2 3 here in equation 2, if we replace the value of f2 3 with this, the newly formed equation would look something like this. It would be f12 multiplied with magic matrix again multiplied with magic matrix gives f34. Now you see, we can rewrite it in the form of this equation: f12 multiplied with magic matrix raised to power 2, which gives us f34. So you see, we multiplied the base matrix which was formed which was a row matrix and was formed using the base k elements of the recurrence relation. If we take that matrix multiplied with magic matrix raised to power some n, then the elements are transformed from f1 to fn plus 1, f2 to fn plus 2, and so on. So if we take the nth power and multiply it with this matrix, we can calculate n plus 1th element. And how we can the complexity of calculating a matrix raised to power some n, we have already seen in the previous matrix exponentiation lecture. The complexity of a matrix, calculating a matrix raised to power n, is actually dimension cube multiplied by log n, and dimension of this matrix is 2, so it would be 8 2 cube into log n, which is 8 log n, which is asymptotically, which is actually log n. So in log n time we are able to calculate the nth element of a recurrence relation. So let's learn more about this magic matrix. Does it even exist, or can we calculate it? So we saw that f1 2 multiplied with magic matrix gives us f2 f3. If I write it down in this form, so f1 so f1a plus f1a plus f2c would give us f2, and f1b plus f2d would give us f3. This is nothing new, this is simply matrix multiplication. So f2 would be f1a plus f2c, f3 would be f1b plus f2d. Now if you analyze this thing, what should be the value of a and c so that the left hand side is equal to the right hand side? If you think for a second, you can come up with the values 0, 1, of course. If I fill the value, or if I replace a with 0 and c with 1, the left hand side becomes equal to the right hand side. So a and c must be 0, 1. Just think about the second equation. What should be the values of b and d? If you think, these come out to be 1, 1. If I replace b with 1 and d with 1, so f3 comes out to be f1 plus f2, and by definition f3 is equal to f1 plus f2. By definition of Fibonacci numbers, f3 is sum of previous two terms, which is f2 plus f1. So if we replace b and d with 1 and 1, so the equation becomes f3 is equals to f1 plus f2, which is true. Hence left hand side is equal to right hand side. So the matrix, the magic matrix is actually 0, 1, 1, 1. And this magic matrix is actually known as transition matrix, which basically you can explain because it forces a transition of elements by I, if you raise it to power some power I. So what it means that you can take the first k terms and you can make a row matrix and then calculate n minus 1th power of this matrix, then you can get the result fn and fn plus 1. So let's analyze the complexity. This would be 8 log n. This would be calculated in 8 log n time, and then multiplication of two matrices would be n cube, so it would be again 8, which is constant time operation. So you can calculate in log n time the nth Fibonacci number, or you can return the first element of the newly calculated row matrix. So this is how you calculate the nth Fibonacci number or nth element of a recurrence relation, which need not to be a Fibonacci series only. To make things even clear, we have seen that okay, if I calculate this matrix raised to power n minus 1, I am going to get fn and fn plus 1. So to test it, just calculate f1 and f2. I have replaced with 1, 1 because fn and f2 are 1, 1. Just calculate this matrix raised to power 3, multiply these two and see if you get f4 or f5 or not. f4 and f5 are 3 and 5, so you get 3 or 5 or not. You'll see that yes, you get 3 or 5. I'm leaving this as an exercise because I want you guys to not just look at the formulas and see okay, this must work, but to actually analyze yourself and see practically whether this works or not. And this have to work because this is actually true. This is actually an algorithm, so it have to be true. Now There we have seen for Fibonacci number, let's find the transition matrix for another recurrence relation defined by me, of course. Fn is equals to 2 times of fn minus 1 plus 3 times fn minus 2. And since the nth term depends upon previous two terms, so the first and the second terms must be defined. So I have defined the first term to be 0 and second term to be 1. Now for this recurrence relation, we need to find the transition matrix. Again, we would start with the same equation. We take f1, we would define the row matrix to be f1, f2. It would be 1 cross 2 size because it depends upon previous two terms. So it would be 1 cross 2 matrix. Since it is of order 2, so the matrix would be of size 2 cross 2. If it depends upon previous k terms, then the size of this matrix would be k cross k. So this is of 2 cross 2 matrix, and it forces the transition of these elements. Now again we would write f2 is equals to f1a plus f2c and so on. Now again, what should be the value of a and c such that left hand side and right hand side are equal? Of course, here we would have to change nothing, replace a with 0 and c with 1. F2 would be equal to f2. Now for the second equation, this is interesting. F3, what should be the value of b and d such that f1 times b plus f2 times d is equals to f3. Now if you look at this equation, f3 would be 2 times f2 and 3 times f1. So f3 have to be 2 times f2 and f2. So we would have d have to be equal to 2 because f3, using this equation, the definition of this recurrence relation, f3 have to be equal to 2 times f2. So since f2 is being multiplied with d, so d have to be 2 and b have to be 3 because f3 is equals to 3 times f1. So b have to be 3. So you see the transition matrix comes out to be 0, 3, 1, 2. This is how you calculate the transition matrix. And if your the row matrix of it, or basically if the recurrence relation depends upon previous k terms, size of this transition matrix would be k cross k. And to calculate the nth number, all we have to do is first calculate the transition matrix, raise it to power n minus 1, and then multiply these two, and then return the first element, which would be the nth term of that Fibonacci number. It can be calculated in logN time. So in the next lecture, first of all about this lecture, I hope you have get it. If not, just go through the video again, or you can read some articles, because after watching a video, reading an article and understanding about it would become much easier. So if you haven't understood it, just go through some articles through Google or on Codeforces, Top Coder, from whatever is your favorite source. You can read about it, you would understand it, and play with these things for a while. Like define the first few terms of it, just raise it some power and see whether you multiply the base matrix with this and you get the result or not. The more you would play with these things, the better it would fit inside your head. So for the next video, we would solve this problem literally. There are some problems on recurrence relations, so we would solve those problems and we would have some hands-on experience on coding for this recurrence relation problem. Till now, keep coding guys, and thank you. Bye.